Hi, this is Garrett at the University of Florida, and I'll be discussing this decision support model that we've been working on to look at different possibilities and options for distributing clean seed to try to help stop the cassava mosaic disease spread in Southeast Asia. So this is work of Kelsey, Andersen Onofre, and a team of people listed here, and it's been part of the research program on roots, tubers, and bananas with CGIAR. So we're thinking about landscape level management of emerging epidemics. So we're thinking about how you can distribute clean seed in a region and not only give a benefit to the farmer who receives the seed, but also reduce epidemic spread as much as possible. So we're thinking about strategies for distributing the seed in the landscape to help slow the spread of disease. So one of our goals here is to make the best use that we can of the often limited data that is available for decision making about questions like where to distribute clean seed. So this is part of the development of a general modeling framework that we've been working on, impact network analysis. And we have an R package available to use it more generally. So the goal of this R package is to provide decision support for regional management interventions like we're talking about here for cassava mosaic disease. So I'm going to talk about this R package for just a little bit and then talk about the specific case for cassava mosaic disease that Kelsey, Andersen Onofre, and others have been working on. So if you're not familiar with network models, the idea is that you're characterizing a system in terms of nodes and links between the nodes. And in the case of a seed system, the nodes might be individual farms or they might be regions, as in the cassava mosaic disease model, we're looking at districts. And then the links indicate something about, in the case of seed systems, the volume of trade or the probability of trade movement between the different nodes in the network. So once we have characterized a network and understand some of its characteristics, we can look at questions using this impact network analysis framework, like how valuable each of the nodes would be for surveillance. So if you imagine these are small seed systems, then the darker shaded nodes would be the ones that would be particularly valuable for surveillance. And then we can extend those ideas to think about not only surveillance, but also mitigation, as in the case of the cassava mosaic disease study. In the impact network analysis framework, we can also look at multi-layer networks. So here, the biophysical network would be the potential movement of a pathogen among farms, if the nodes are farms here, or districts at a larger scale. And then the socioeconomic network would be the people who are making decisions about whether or not to use a particular management on a farm, such as clean seed, and influencing each other about that decision. And then the combination of these systems of the human decision making and the spread or potential spread of disease then will determine how successful disease management is in a region. So this framework in general can be used for questions like this. So what locations are particularly important? And that's one of the things we're looking at with CMD. How are the benefits distributed to people, for example, in terms of traits like gender or age? How could policies or other types of subsidies influence system outcomes? So we're looking at that in terms of the best locations for distributing seed. And then you can also ask questions like whether the observations are in line with the goals for project monitoring and evaluation. So for thinking about cassava mosaic disease and its spread, so this paper describes some aspects of spread through seed systems in Cambodia and Vietnam. So once we start to understand these structures, we can understand better the risk of movement through the different geographic regions. So we can think about, for cassava mosaic disease, spread within and between fields at a smaller scale, right? So that's going on in the landscape within a district, for example. So that spread could be through the whitefly vector between fields. Then we're also looking at the spread through trade, and we can consider both formal and informal seed systems. And then also Kelsey, Andersen Onofre and this team incorporated habitat suitability for establishment. So looking at the environmental factors that would make some locations more likely to have the pathogen established than others. So combining these gives us a broader look at the system. Yeah, so trade will dictate the arrival of the virus, but then the environmental suitability will dictate establishment. So in this case, Kelsey, Andersen Onofre and the team looked at species distribution modeling to develop a map of environmental suitability for CMD. And then we can combine that with the information about trade and potential movement among fields for a more complete analysis. So thinking about the habitat suitability, here's the modeling pipeline that Kelsey and the team used. So we've got a set of climate variables, monthly climate data, land use, etc. So all these are potential predictors for suitability. And then using machine learning tools, looking at which are the most important predictors for risk of establishment, and then combine that with the network models based on trade and field-to-field movement within districts. So here's an example of a preliminary prediction of the risk for cassava mosaic disease at the district level. And we're still finalizing this and can provide a final version of that risk based on the most recent data soon. So here's an illustration of the considerations in this model. So suppose each of these circles represents a district, and there can be exchange between these, and then we're also looking at how much cassava mosaic disease there is in each district. So exchange may occur along these routes indicated here, and over the course of time, disease levels may go up. And then if we focus in on what's happening within a pair of districts that have trade occurring between them, so within season, there can be spread between them, and there can also be additional disease buildup within a district. So if these are districts, we can think about the healthy hectares within the district and the infected hectares, and also for this other neighboring district. So there's the potential for the spread of disease between them. And then within a district, there's also the potential buildup of disease. But then also if healthy clean seed comes to that district, then there's the potential for the infected hectares to go down with the added clean seed to the region. And so then using the model can simulate disease spread over time and look at how different types of management are likely to work in the context of it. So here's just an illustration of what that can look like in one simulation. And then what we have focused on then is this question about disease-free planting material. So there are going to be limits on how much can be produced within a year for distribution across a country. So then the question is, what's the best way to deploy this seed? So here we're looking at three methods. So one potential that's really just more for comparison of the others is random selection of locations in the regions with cassava mosaic disease and nearby, because the disease might have already spread further than it has been detected. So that's more of a reference point or check for what might happen, this random selection of locations. And then a second type of approach then is to target consistent selection of locations where the highest CMD levels are present. And then a third option is to keep changing that as new locations with higher cassava mosaic disease are detected. We're also considering some other potential management strategies and welcome input about the practicalities of management as well to make the scenarios that we're testing as realistic as possible. So we're continuing to develop this in collaboration with a team that I mentioned at the beginning of the presentation. We look forward to input from your discussions at this meeting, and we'll also be happy to discuss the next advances in the project as we finalize this first phase. And then in terms of this R package that we're working on, we have this existing version that's available from this 2021 version of the R package that was published here. And then we're also preparing a next version of the package to support clean seed distribution and to make it easy to adapt the model described here, developed by Andersen Onofre et al., to new scenarios and new data available about cassava mosaic disease and other systems. So we look forward to opportunities to discuss this further, and thank you for your attention. Be happy to discuss this further with anybody who would be interested in giving input and discussing other options.